Hi, this is implementation of Visual Transformer. We're going to use NanoGPT by Karpathy as a basis point, and it doesn't need any introduction. And if you want to get more into detail, then I encourage you to check out these materials by Daniel Brook, which cannot be recommended enough. So assuming you've set up the environment, you should have no problems with all those imports. And you can get the Shakespeare dataset and define some utility functions. And then this is where the architecture of NanoGPT is. There are only some cosmetic changes from Karpathy's video, like the global concepts are capitalized and some classes are renamed. One difference is introducing this isDecoder variable, which determines whether the triangular mask in attention mechanism is active or not. So it is implemented for the decoder because you don't want the token at position X to know about the tokens that follow it, only the ones that precede. But this is not necessary in the encoder. So with the architecture defined, we can proceed to train the NanoGPT, and we can see that originally it generates some rubbish output, but hopefully that improves after training. Fast forward a few minutes, we've trained our NanoGPT and it generates some output like Merry Christmas, would of thee, and nothing serve under that word deal, whatever that means. So we can now proceed to the NanoVIT, and the first step is again getting the data. So we're going to use MNIST dataset, which is readily available, and then we're going to normalize all the images, so that's what they look like. And now we can proceed with the Visual Transformer implementation. So the first step is defining this patch embedding layer, and this patch embedding layer is required for the VIT transformer to work. So the main difference actually between the NanoVIT and NanoGPT is that we use patches of image as input tokens to the transformer. So we take the image, we split it into patches, and then we embed them using this convolutional layer. That's why we have patch size and as both kernel size and the stride, and then the embedding dimension is the number of the output channels. So with this, we can inspect how different bits of how shape of the image looks like at different steps in the algorithm. So we start with the images of one channel and 28 by 29 sides. This is the patch dimension. Then once we embed them with the patch embedding, they become 16 by 128. 128 is the embedding dimension, 16 is the number of patches. And then another thing is that this 16 changes to 17 because we prepend the class token to the input. This is the equation 1 of the VIT paper. So here all these guys are the embedding of the image patches. Then we prepend the class token, and then we add the position embedding exactly as we did with the NanoGPT here. And then we can pass this through the multi-head attention and MLP head, and everything seems to work, at least in terms of shapes. And now we are good to go and take our simple decoder as is and adapt it to become a visual transformer. So we start with changing the token embedding to use the patch embedding we defined above, and then position embedding now becomes patches plus 1, and then we need to define the class embedding. So we do that as follows. And then importantly, in the transformer block, now specify decoder equals false because we don't want the triangular matrix in the masking in the similarity matrix. And then our output size becomes num classes for the 10 digits in the MNIST dataset. In the forward, we no longer need these two guys. The token embedding remains as is, but the position embedding now is num patches plus 1. Again, we need the class token, and for that we use the class embedding expanded to batch size, and then position embedding now use a combination of class token, token embedding is now a combination of class token and token embedding concatenated. And that's that. So now looking at the equations 2 and 3 of the VIT paper, if we look at our NanoGPT architecture, then we'll see that they're actually already implemented exactly as we want. So we pass inputs through the layer normalization, which then is passed through the multi-head attention and combined with the residual connection input here. And the exact same thing is done for multi-layer perceptron in equation 3 here. So that leaves us with equation 4 of the paper, where we take the class embedding and pass it through a layer normalization. So this is what we do here. So after x has passed through our attention, we take the 0th entry of it, and we're pretty much done, except we no longer need these guys. And of course there is no generate function either. And with all that, we should be good to define our simple VIT model. And once that is done, we can proceed to train it, pretty much using the same training loop as we used for GPT. Fast forward, our training is complete, and this is how our predictions look like. And that was Visual Transformer in under 10 minutes. Thank you.